Hey, how's it going? Is this suitable for Year 12 students doing AS? That's a good question. So I guess it's some general various questions. Hopefully I'll be able to introduce the concepts as we go. So yeah. Can I use some mechanics tips for physics? Yeah, I can give some tips as I go along. I'll just see remind myself what questions we've got for today to go through, because it's going to be all sorts. Let's see. Yeah, there's not loads of. Yeah, so there's a bit of mechanics, but in the kind of physicsy context where it's a lot of doing mechanics with energy and stuff. Tips on electricity. Yeah, so we've got a potential divider-ish style question for today. Only a nasty resistor in parallel with a resistor. So we're going over like loads of different exam questions. Well, things like this will hopefully help. Lots of practice. It'll be about an hour. We'll get going in just a sec. We'll start at 5 past. We are going over all sorts of units. Just a general kind of spattering of exam questions. Yeah, there's a lot of the stuff in physics is really hard to kind of wrap your head around first couple of times. Yeah, hopefully this will help. Okay, should we get started? I'm just gonna slam through some questions. Yeah, so this is for all exam boards. So yeah. Okay. So hopefully very soon everyone will be able to see my slideshow. Is that right? So it's both year 1 and year 2. Okay, so we're going to look at some mock exam practice technique questions. Just see how we go. So I'm Matt, head of physics at SnapProvise, physics PhD student at the moment. And I've been tutoring A-level physics for the last 4 years or so. What's the aim of this web class? So this is an opportunity to practice questions together and cover some key exam technique in preparation for your mocks. So we're going to look at kind of, before you want to even you might notice that like half the problem is like trying to answer a question. Sometimes half the problem is trying to figure out like what the question is. So like we'll do a bit of like question analysis, really trying to like read a question and get the meaning from it properly. We'll talk a bit about languages used in mark schemes. Again, exam technique, which is similar, and we're going to cover a range of questions. There's no particular unit. Yeah, it's about an hour. So there's going to be some giveaways at the end of this tutorial. So we're giving away a free account for one. all you need to do is follow us on Instagram and share a picture of the web class on your story. And generally, we have a one-time big discount codes for anyone who stays to the end, which I'm sure will be all of you. Okay, so let's start by having a go at a question. So this is a warm-up question. The following is a list of scalar and vector quantities. So acceleration, density, displacement, energy, power, speed, time, weight, all the main quantities you ever seem to come across in physics. In the blank spaces provided, list the quantities as either scalars or vectors. So what do we reckon? Let's start with acceleration. What do we reckon? Acceleration. Acceleration a vector or a scalar? Yeah, absolutely right. Vectors. So what is a vector? A vector, well, a scalar is a thing that is described by a number. And then a vector is a thing which is described by both a number that says how big it is. Oh, guys, you guys are smashing it. Just a number that describes how big it is, and also a direction. So acceleration, we always say our acceleration in a particular direction. So acceleration is a vector. Oh, vector? No, acceleration. What a start. Okay, cool. Hello. Can everyone hear me? Are we back? I'm not sure what happened there. Good. Okay. Well, apologies for that. Right. So we were talking about density. So do we think density? Yes, I'm Matt from GCSE physics. Okay. Density, vector or scalar? What do we reckon? Vector or scalar? Scalar. Good. Okay, so let's just remind ourselves. Density is mass over volume. Okay, what's mass? Mass is a scalar. It's just a number. It says how much stuff you're made of. Volume is a scalar. It says like how big something is. We're dividing two scalars by each other. We get a new scalar. Okay, density. Okay, so we're going to fill a couple more of these in. I'm going to leave displacement alone for now. I'm interested in energy, power, and time. What about those? Energy, power, and time. Yeah. So I think the hardest one to think about here is maybe time. You sometimes imagine time having like a direction, but it's just a number. So it's just a scalar. Energy is just a number. Power is energy over time. Okay, so we get a load for free here. Energy, time, power. Okay, so we're really stacking up on the scalars. What about speed? So it's going to be a mixture of AS and A level. Yeah, well done. Well done, everyone. So, speed, what's speed? Yeah, speed is a scalar. Can anyone think of a vector version of speed? Vector version of speed. Yeah, speed is a scalar. Is there an associated vector? Ah, yeah. So power, why is power a scalar? Okay, so power is equal to energy over time. Now, time is a scalar and energy is a scalar, i.e. they're both just numbers. And when I divide two numbers together, I just get a new number, a new scalar, and that's power. Yeah, absolutely right. So velocity would be over here. I'll put it in brackets. If they'd have asked, we'd have said velocity. Okay, good. We've done speed. What about weight? It's kind of a funny one. Where's weight? You think of weight as being how heavy you are. Is that a vector or a scalar? Thank you. Yeah, I wrote that on the wrong side. Cheers. Speed. Good. Weight is a vector. This is a kind of funny one. So mass is like the scalar version almost. Mass is like how much stuff you are, but the force is like weight is the force due to gravity on a particular mass. And force is a vector, so weight is a vector. Okay. Weight. And that leaves displacement. What do we think for displacement? Yeah, absolutely right. Okay, good. Well done, everyone. So that's us warmed up. Let's have a go at this question. So, a supertanker, whatever a supertanker is, of mass 4 times 10 to the 8 kilograms, cruising at an initial speed. So here, as soon as I start looking at a question like this, even though this might be a kind of a simpler one, like I basically write down symbols for the things I'm being told as I go. Kind of helps me keep track of the question. So they say mass, they tell me this mass and I say, okay, m equals 4 times 10 to the 8. I've got that kind of stored in the bank now. Initial speed of 4.5 meters per second. Okay, let's call that u for initial speed. 4.5 meters per second. Okay, takes how long? 1 hour to come to rest. So time equals 1 hour. Cool. Okay, assuming the force slowing the tanker down is constant, calculate the deceleration of the tanker. Okay, so what's acceleration? Yeah, good. So you could think about this in Suvat. What you would end up doing ends up being the same as the actual definition of acceleration, which is change in velocity over time. So what's the change in velocity here if we started at 4.5 and went to 0? So the acceleration is defined as change in velocity over change in time. How long did it take? Well, it was 1 hour. So that's 60 minutes and each minute is 60 seconds. Good. And the change in velocity is 4.5. And in fact, it's minus 4.5. We went from 4.5 to 0. Good. Okay. So what does this give us? So you should get 1.25 times 10 to the minus 3. 10 to the minus 3. And the units, never forget the units. Hello, are we back? Really sorry about the technical difficulties. I'm sure we'll be back on track in a second. Okay, really sorry about the technical difficulties here. Let's have a go at the next question. So we want to know the distance traveled by the tanker whilst slowing to a stop. And everyone who was talking about Suvat before, absolutely great shout here. So what do we know? Whenever we do Suvat, we should write down all of the variables that are involved in a Suvat equation. We pick out the one we want to know. Then we write down all the other variables that we know. So we know the initial velocity. We in fact know the final velocity. What was the final velocity? Yeah, that's right. So the final velocity was 0. We decelerated all the way until we came to rest. Then we have the acceleration. And the acceleration we just calculated. So that might come in handy. 1.25 times 10 to the minus 3. Cool. And do we know the time? We absolutely know the time. The time was 3,600 seconds. That's 60 minutes times 60 seconds. Great. Okay. So what can we do? Can anyone think of some versions of the Suvat equations that might help us out here? Well, I can think of a couple of versions. So you have a lot of choice here, which is nice. We're going to use the acceleration we already calculated and use the equation v squared equals u squared plus 2as. So how's this going to help us? Well, we know v squared and we know u squared and we know a, so we can just rearrange for s. Now, it's always helpful to rearrange your formula before putting the numbers in, because that helps you keep track of any mistakes when you go back and check. So this says s equals v squared minus u squared all over 2a. And if we plug our numbers in for u, for v, okay, so v is 0. Good, okay. Then you should find that our displacement is roughly 8.1 times 10 to the 3 meters. Good. Okay. So let's have a look at another question. So the next part of this question asks us to sketch using the axes below a distance time graph representing the motion of the tanker until it stops. Okay, so we're being asked to plot a distance time graph, and there's going to be one really important thing here, because we haven't really done much to do with distance in this question yet, but we've been told a lot of information about velocity. So my question is, how can we find out the velocity if we've been given a distance time graph? What do we reckon? Have we got any ideas? So just seeing through your comments now. Okay, great. Yeah. So the gradient of a distance time graph is velocity. Perfect. So how does the velocity start? Well, we know the velocity starts off at, and let's just check our number. The velocity starts off at 4.5 meters per second. And the velocity finishes at, say, 0 meters per second. Meters per second. So the gradient starts off at 4.5 and goes down to 0. So to start off with, the gradient is steep and positive. And when we finish, the gradient should be 0. Now, what does a line with gradient 0 look like? Does Has anyone got any ideas? A line with gradient 0. Yeah. Okay, so a line with gradient 0 is a flat line. Like, so if you start off flat, that's gradient 0. This is a positive gradient. This is a negative gradient. So we know we finish with a velocity or gradient of 0. There's 0, flat line. And we know that since we're decelerating, our velocity is decreasing. So the velocity, our velocity is decreasing. Therefore, our gradient of our graph is decreasing. So it's getting less and less steep until it goes flat. So that's a nice distance time graph. It's quite a good conceptual question, that. Hello, apologies for that. Don't know what's happening tech-wise today. Try and get us back on the road. So where were we? So the velocity is decreasing from a Okay, so I believe we're back. Apologies again. Let's have a look at another question. So this is a completely different vibe of question. An atom of argon 3718 Ar is ionized by the removal of 2 orbiting electrons. Okay, so there's a lot of things to think about there. Be nice to kind of understand what these numbers mean to start with. And in fact, the first question says, how many protons and neutrons are there in this ion? So does anyone know what this bottom number here represents? What's that bottom number? It's the smaller of the two numbers. So that's interesting. Yeah, so this one counts the number of protons. It's called the proton number, or the atomic number. So in fact, we know straight away that we have 18 protons. This number at the bottom counts the number of protons. Awesome. So What about this top number? What's this top number? Okay, so this top number is called the mass number. Mass number. Okay. So great, that's a word, but what does this word mean? Yeah, so this mass number, yeah, good, is the number of protons plus the number of neutrons. So if we know the number of protons plus the number of neutrons is 37, and we know the number of protons is equal to 18, then do we know how many neutrons we have? What do we reckon? Do we know? Yeah, so it's 19. 37 minus 18. Total number of protons and neutrons, take away the number of protons, gives me the number of neutrons. Awesome. 18 protons, 19 neutrons. Notice how there's usually a similar number of protons to neutrons. That kind of changes as atoms get bigger and bigger and bigger. But for smaller atoms, they tend to be similar. So what's the charge of this ion? Of course, this is not an atom. This one is now an ion. So what's the charge? We've removed 2 electrons. Okay, good. So the first thing we need to know is, what is an atom usually? An atom usually has a load of positive charges in the center, all these negative electrons flying around the outside. Okay, well, not actually flying, but you can sometimes imagine them as kind of orbiting around. And the point is that for an atom, it's neutrally charged. So the amount of positive charge in the middle balances the negative charge going around. So we remove 2 electrons, which means there's 2 extra positive charges in the center. Before there was the same number, now we have 2 less electron charges. So we have a charge of +2 on the ion. We've taken away 2 negative charges because electrons are negatively charged. Good. Okay. So which constituent particle of this ion has a 0 charge per unit mass ratio? What do we reckon? 0 charge per unit mass ratio. So okay, sorry about that. So where were we? We were just going through the charges of the various, what we call subatomic particles. Why subatomic? Subatomic. So they're kind of beneath an atom. They're actually the things that make up an atom. They're more fundamental than an atom. So we have a proton, and a proton has a +1 charge. Now, what about the charge of an electron? Yeah, so the charge of an electron is opposite to the charge of the proton. We kind of mentioned this in the last question. So the charge of an electron is -1. Okay. And finally, what about the neutron? Now, the clue is in the name, neutron. So this bit here kind of stands for neutral. It's neutrally charged. It has no charge. So it has a charge of 0. So which one of these has 0 charge per unit mass? Well, a neutron has some mass, but it has 0 charge. So the charge per unit mass is 0 over its mass, which is 0. Okay, so it's the neutron. Which one has the largest charge per unit mass ratio? Well, it's going to be a toss-up between the proton and the electron. So they both have the same size charge, but which one has the bigger value of charge over mass? Well, we can increase the value of charge over mass by decreasing the mass. So which one of these has the smallest mass? Well, that's the electron. Good. Yeah, good. Electron. Good. Okay. And finally, we're asked to calculate the percentage of the total mass of this ion that is accounted for by the mass of its electrons. Okay. So what do we reckon? First of all, how many electrons do we have? We're going to want to take the mass of the electrons. We want the percentage. So the mass of electrons, which is going to be the number of electrons times mass of each electron. And we want to divide that by the total mass. That will give us the percentage mass that the electrons are contributing. If we times by 100, you make the fraction, you always times by 100 to get a percentage. Okay, so how many electrons do we have? Do we know? Okay, good. So we know that originally we were dealing with our atom, and it had, what was it, 37 and 18. So this number here is proton number, but it also tells you, because the atom should be neutral, it tells you the number of electrons you would have had when you started. But we've made an ion by taking 2 electrons away. So we must have 16 electrons. So we take our 16 electrons, then we need to multiply by the mass of 1 electron. So does anyone know the mass of electron? Good thing is you will be given this in your formula book, so no worries if you don't. In fact, I can never remember this. So the mass of the electron is 9.11 times 10 to the minus 31 kilograms. Okay, what about the total mass? Well, let's find the mass of the neutrons and protons. So how do we find that? We know that roughly each proton and neutron weighs the same. Each proton or neutron weigh like 1 atomic mass unit roughly. And so around 1.67 times 10 to the minus 27 kilograms. Notice that that looks small, but it's like 4 orders of magnitude bigger. You'd have to times this by like 4 or 5 or divide this by 4 or 5 lots of 10 to get anywhere near how small the mass of the electron is. So compared to the electron, these things are really heavy. Okay, and how many of them do we have? Well, in the ion, we never removed any protons or neutrons, so we still have 37. Good, okay. So we know we have 37 lots of the mass of each proton or neutron. 67 times 10 to the minus 27. kilograms, kilograms. Always nice to keep track of your units. Now, of course, we should have actually added in the masses of the electrons again here. We're trying to find the electron masses over the total mass. But since the electron masses don't really contribute much to the total mass, we can just use this number here. We'd be adding on a teeny tiny amount if we added on the masses of the electrons here as well. Okay, so if we plug this in, then we should get around 2.36 times 10 to the minus 2%. So if you do that fraction, you should get 2.36 times 10 to the minus 4. We times by 100 to get the percentage. So this is tiny, absolutely tiny. These electrons contribute almost no mass, which is why they have such a large charge per unit mass ratio. Good, okay. So I know there was a request for some mechanics, so let's have a crack at a mechanics style question. But whereas in like mass mechanics, you do a lot of velocity, acceleration, Suvat, whatever, in physics mechanics, you do that, but you also chat a lot about energy. So imagine that we have this egg, an egg with a mass. So of course, the first thing we do when we see this sort of stuff is we try and write down what we've been told so that we don't forget. So mass equals 5.8 times 10 to the minus 2 kilograms. Okay. What else do we know? So we know that we've been dropped from a height, let's call it h, a height of 1.5 meters. That's quite a nice number. Assuming no air resistance, calculate for the egg the loss of potential energy. So of course, when they say the loss of potential energy, they mean from when we dropped it to when it hit the floor. So what type of potential energy are we on about, and what's the formula? Do we know? If we drop something from a height, it's or if we lift something up to a height, what kind of energy are we giving it? We have to kind of use like chemical energy, like from our limbs to be able to push this thing up. What are we giving it? Well, what makes it hard to put it up there? Gravity. So we're working against gravity, we're giving it gravitational potential energy. So what is the formula for gravitational potential energy? Yeah, absolutely right. Okay, so formula for gravitational potential energy. Good, so this is m times g times h. And so as long as we know g, and I'm pretty sure we know g, that's 9.81, we've got all of the numbers we need to plug into our equation. So let's do that now. So you should find, if you plug these three numbers in, that we get 5.8 times 10 to the minus 2 times 9.81 times 1.5. And that should give you 0.85 joules. That's a kind of disappointingly small number, I think. But hey, we're only dropping an egg. If we wanted more energy, we'd have to drop something heavier. Because if we drop something heavier, it'd have more mass. And more mass would mean a larger gravitational potential energy. Okay, so what's the kinetic energy just before impact? This is a one-line answer, which is a hint there might be something clever we can do. So what do we reckon? What rule are we going to use? Yeah, so why do we even care about energy? There's all sorts of quantities we could calculate. We could calculate m squared times g times h or something. But energy is an interesting thing to calculate because it's conserved. So energy is conserved. since energy is conserved, we know that all of that gravitational potential energy we lost must have gone somewhere. And where has it gone? Well, none of it was lost to air resistance or anything, because that was negligible. It must have been converted into kinetic energy. And in fact, that makes sense. We dropped it from rest and it got faster and faster and faster as it fell to the floor. So it was gaining kinetic energy. Its velocity was increasing. So all of the energy is converted into kinetic energy. Good. Okay. So now what about the speed just before impact? Okay, so now we have to actually think about what kinetic energy means. So does anyone know the formula? And it's kind of hard to type these things into the chat window. Find your favorite way to do it. How do we find the kinetic energy? Good. Okay, so the formula. We always start with a formula. Always makes it easier to check your work. Like if you just slam straight in with the number and then you try and go back to the exam at the end, it's really hard to figure out what you did. So write the formula first, you can't go wrong. And if there's more than one mark available, the examiner might give you a mark for the formula. So we want to know the speed, so we got to rearrange. So I'm just going to use the symbol E for kinetic energy. If we rearrange this, we find V equals the square root. Well, let's do this in steps. So V squared equals 2E over M. So V equals the square root of 2E over M. Notice how I always rearrange things in algebra with letters first. Again, so much easier to check your work. And then we can plug our numbers in. We know the energy and we know the mass. So let me know what you get. See if you can beat me to it. So 2 times 0.85 divided by 5.8 times 10 to the minus 2. Good. Okay, and we should be able to get a number out of that. So what number do we get? Has anyone got a calculator with them? Aha. So we should find V is around 5.4 meters per second. Good. Okay. So now finally, we're being asked, what's the momentum just before impact? Okay. So does anyone know the formula for momentum? We give it the symbol P, which might help it kind of help trigger the memory of the formula in your head. What do we reckon? Good, yeah. So momentum is equal to mass times velocity. Okay, so let's just jot that down. So momentum is equal to mass times velocity. Okay, so what's the mass? We know the mass and we calculated the velocity. So this is perfect. We can just plug our numbers straight in. We've got 5.8 times 10 to the minus 2 multiplied by our velocity, which was 5.4 meters per second. So let me know what momentum you get. And you should get around 0.31. 0.31 Newton seconds. Newton seconds because it's force times time. It's another way to think about momentum. Good. Okay. Let's finish off this question, shall we? Yeah, let's do it. So On hitting the floor, the egg is brought to rest in a time of 0.01 seconds. Calculate the magnitude of the average decelerating force on the egg. Well, it feels like there's a lot there. So we know a time. Always write it down. Seems silly, but just helps me think. Time is 0.01 seconds. Okay. Calculate the magnitude of the average decelerating force on the egg. Okay. So we found a momentum before. So can anyone think of a relationship between force and momentum, maybe? So almost kind of a definition of force. Maybe it's not the way you'd usually think about force. How is force related to momentum? What do we think? Yeah, so force is rate of change in momentum. It's change in momentum over time. So we know the time interval over which our momentum, well, let's think about this question. Why are we interested in momentum? Hitting the floor, it's brought to rest in its time. So we calculated the momentum just before it hit the floor. So just before it hit the floor, it had a momentum of p equals 0.31. Now, it's brought to rest. And what's the momentum when we're at rest? Well, momentum equals mass times velocity. So when it's brought to rest, the momentum must have changed to 0. So somehow in this kind of impact with the ground, the momentum went from 0.31 to 0. And if we know the time it took for that to happen, we have the change in momentum over the change in time, and we'll be able to find the force that caused that change in momentum. Okay, so let's plug in our numbers. We have 0.31 divided by 0.01. It should give you, it's like dividing by 0.01 is like timesing by 100, isn't it? Yeah, good. So without even a calculator, this is 31 newtons. Okay. So let's take a look at the last part of this question then. So the last part of this question says, the egg is now placed in a container that crumbles on impact. Explain why this type of container makes it far less likely that an egg will break. So why would an egg break? If you wanted an egg to break, how would you do it? What do? You'd throw it at a wall or something. It's kind of what we're doing here. We might drop it on the floor. Or something else you might do is just like hit the egg. The idea is we can break an egg by exerting a force on it. If we exert less of a force, then it's less likely to break. Now the force is the change in momentum over time. That's this formula here. So let's put that in. This is going to help us. Force is change in momentum over time. We know just before it hits the floor, it's going to have this momentum, 0.31. And that's got nothing to do with whether it's got this kind of crumply container or not. But what's going to happen to the time over which our object goes now from our initial momentum to 0? What do we reckon? Okay. Yeah, so if this thing crumples on impact, imagine like maybe less like something that crumples, maybe you can imagine some kind of like sponge or something that was around the egg. If you had like a spongy surface, then as it hit the ground, there'd be a bit of time where it kind of compresses rather than, and that kind of bit of compression time there before, in the other case with just like a hard egg, it just, as soon as it touches, it needs to be stopped immediately. So this kind of crumpling bit gives us some extra time to change the momentum. So it increases the change of time. So here we would say the time over which the momentum changes is increased. So the force on the egg should decrease. And that's why the egg is less likely to break. Great. Well, well done, everyone. Good. So let's just take a look at what we have left. So I really want to do is take a quick opportunity to take you around the SnapRevise site, because we do loads of these sorts of things, all sorts of stuff that you might be interested in. Yeah. I'm just going to bring up a new page now. Great. So I'm going to log us into snaprevise.com. I hope you enjoyed the session. I'm sorry about the technical difficulties we had along the way. I hope you still were able to learn something through that. Okay. So I'll just get up SnapRevise for us. snaprevise.co.uk. So one second. My apologies. Having a quick struggle here. Sorry about this, guys. Just one second. Okay. Here we go. Okay, so my apologies for that. We're now on the SnapRevise website. So if you want to see more of this kind of stuff and all sorts of intelligent learning kind of processes that will help you get those A's and A-star grades that you're looking for, and if you just want like a really fun way to kind of learn the learn the concepts that you're trying to get through at school, and you want to see them in kind of a different light, then we've got these kind of bite-sized videos, kind of manageable chunks for learning things with like exam questions and quizzes in between. So I'm going to take you through quickly what we have. So to start off, let's sign up together, because it doesn't Doesn't take anything to sign up. So here we go. I'm going to say I'm a student. I guess I still am in a way. So what name am I? Okay, let's say I'm Matt from Snap Revise. Yeah. Okay, we'll make some new email. Snap Revise demo. Good. Okay, I have to make up a password. You can't see this bit. Okay. Oh, say what school I'm from. Well, I'm from Snap Revise. That's my school. And I suppose I'm closest to year 13. Okay, so we can sign up. As soon as we sign up, we're asked to add the kind of subjects we're interested in learning about. The nice thing about this is there'll be some kind of free stuff that you can try out when you sign in and see what you think. I'm sure you'll love it. So let's say we're doing physics. So I know everyone here loves physics. Now, what's everyone's favorite exam board? Yeah, it's whichever one you're not doing, right? Okay, let's go with Excel because it's in the middle. Let's go. Okay, we're shooting for an A star, right? Why not? Good. Last step, which of these best describes you? Well, you pick whichever one you want. I personally am looking for a smart and interactive resource. I do also find it hard to stay motivated when revising though. Okay, so we're in. We have all sorts of interesting things we can do. I know one of you at the start was saying that you were interested in learning more about mechanics. Well, if you go to the Edexcel trial, then you will find some quizzes that will help you figure out how you're doing with mechanics. So let's take a look. We're going to take a diagnostic quiz. So what's a diagnostic quiz? I don't know what it's like for you guys, but when I did my A-levels, like there was a lot of hard stuff and I learned like a fair bit of it and felt like I understood quite well. And there was a load of stuff that I kind of almost subconsciously just didn't look at. I was like, it was stuff I didn't understand so well. Maybe I'd skip over it every time in the textbook. And I'd always go over the stuff. I'd get better and better at the stuff I was already good at. But the good thing about diagnostic quiz is it kind of tells you in your face which bits you're doing well, which bits you're not doing, and then immediately suggests what you need to do to clear up the stuff that you weren't before doing so well. So this would have been really handy for me when I was doing my A-levels because I was too cheeky. I didn't want to do the stuff I couldn't do. So let's start the quiz. Which of the following is a vector quantity? Oh, well, we should be smashing through this. Okay, which one of these is a vector? But momentum has a direction as well as a size. Let's go for that. We won't get all of these right. So which of the following statements about distance and displacement is true? Displacement is a scalar quantity while distance is a vector. That's the wrong way around. Let's just say it anyway. Cool. Okay, an Aston Martin is traveling. Well, okay, 8/6 is like a 3/4. Okay. 2 arrows. Let's just say something random for these. We just want to get through and find out what we're good at. Whoa, what a guess. I'm not even reading these now. What's the magnitude of the sum of these two vectors? Okay, it's like √2 add √2. 2√2, yeah. Okay, no, no good. 20 is the first answer. Okay, we got to get this one right. Actually, no, this one looks too hard to get right quick. Yeah. Oh, this one, we can get this. What's the correct expression to find the vertical component? Okay, Fy/F is sine theta. Yeah, so it's this. Cool. Okay, random guess. Random guess. Whoa, yes. Okay, so you do one of these diagnostic quizzes and you get back some results. Amazingly, we got 50% there. So let's take a look. It tells us what we know and what we don't. So we know, well, we know scalar and vector quantities. But yeah, so it's tested us on each of these 12 things. And it tells us the 6 things that we were less comfortable with. representing vector direction, subtraction of perpendicular vectors. Yeah, funnily enough, the ones we don't know look harder. Simple vector resolution calculation. Okay, so we might think, great, okay, what do we do? Well, this is the beginning. This is not the end. So we don't just find out we don't know stuff. We get immediately taken to a page with all of the snap revised content, and it shows us, okay, there's Kate, our A-level physics expert. Great. We'll just pause her for now. So we get given a series of videos which are suited to the things that we so far didn't understand. And in fact, we see this timeline at the bottom here. So this is really cool, because sometimes you might be watching a video and you might think, I know this bit. When is the bit I don't know going to come? And then you get bored and then you switch off, and then the bit that you wanted kind of went, and then you scroll back or whatever. No worries. So this timeline here shows you in green the bits that you already knew and were good at, and the bits in orange that you might want to improve on. So this is super handy. So you can click to the start of the section that you need to read. Like, we needed to see some examples. We can go straight to there. We didn't need to see this section of magnitudes. No need. But we did want to see representing vector directions. And there we are on the video. So this is really handy for like streamlining it. I know that it's hard to find the time. It feels like it's hard to find the time to do all the stuff you need to do. But part of this is about being efficient with your learning. And this allows you to really nail down on just the stuff you don't know. Clear up, tick off all the boxes that you need to tick off. Okay, great. So you might kind of do this stuff and then you might think, cool, but have I actually got any better? Well, there's another quiz you can do right here. So you can have a go at another scalars and vectors quiz and see how you perform. And if there's still bits that you're struggling with, it will show you again which bits to go back to and go through again. So it's a really efficient way of just ticking off everything you don't know, which is perfect. Gives you more time for all sorts of other fun. So finally, you get to really test your knowledge by looking at some scalars and vectors exam questions. So again, you can take a look at these questions. Let's just scroll through. Yeah, so here's some exam style questions. All the sorts of things you'd be asked in an exam, the real way to test how you're doing. And you can have a go at each question if you want on your own first. So pause the video, have a crack, and then hit play and see if you agree with our physics expert. I'm sure if you've watched our videos and you've gone through the quiz, then you'll have a really good chance of agreeing with them. So we also have this kind of on-site tutor support. So depending on your membership, there will be a comment section available to you at the bottom where you can ask directly about problems you're having. So you can look at a video, and if you're confused about something, you can ask a question about it. And this is great. This is kind of like, this is like having a tutor, I guess. You have a personal conceptual ones as well, not just like exam solutions and so on. This is really nice because, I mean, also it's kind of almost more on demand. But when you compare this to the kind of price and experience of having a kind of like a standard, what we typically take as like a standard tutor, where you might pay, what, I don't know, 40, £50 a session. Well, the most expensive Snap Revise version is less or equal to the tutoring rate for an hour for a whole month. So you get all of this stuff. Okay, great. So these were videos, and there was in here, along with everything else, we had an exam question in there as a video, but we also have the exam packs. So these are a series of questions that we can take a look through. And this is really nice because they, you know, when you're going through the mock exams, you get up like a tab for the exam and then a tab for the mark scheme. You keep flicking between them. Nice interface here where you read the question, have a crack, and then this box here, you can click on it when you're ready, and it gives you a solution in a very attractive font as well. Look at that. Yeah. Okay, so loads and loads of questions for you to answer. And we're going to be uploading more and more exam packs as we go through the year. So things are only going to get better here. Good. Okay. So last of all, let's take a look at the plans. So yeah, as we were saying, a tutor can cost up to £50 an hour. For our service, so we have the basic service for £10 a month. This is fantastic. You get all our teaching videos, you get those exam walkthrough videos that we're talking about. You also have access to our revision guides. For the pro membership, you had all this stuff. Then you get this intelligent learning bit, the bit that really makes things efficient by telling you externally what it is that you need to most urgently work on. So this is super handy and it will save you loads of time. So you get these self-marking quizzes, which redirects your learning. From the self-marking quizzes, you get this smart adaptive learning that we're talking about. And we also get the exam packs, and in particular, we kind of tailored around the things that you're struggling with. So there's these predicted exam packs. So there we go. Take a look at this. Predicted. Yeah, so these are specifically designed based on past paper themes and patterns. So not around you, sorry, but around previous past papers. So I know we all spend time doing that game where we look back over past papers and try and figure out what we reckon is coming. So we've had a go at that game as well. And those are our results. And finally, for the ultimate package, and there's some really cool stuff in here. So you get this smart adaptive learning and all that, but you also get web classes like these, which aside from this one here, mine have never had any of these technical difficulties, I promise. So we have kind of teaching style ones where we go through a topic that you may or may not have seen in school. So if you've seen it in school already, it's a great chance to go over it and see it in a new light. If you haven't been over it in school already, then fantastic. This is a way to get a head start and get a kind of conceptual introduction to what's going on. Because sometimes you can do all the maths, but it'd be hard to get a picture of what's really going on in your head. And the great thing about these web classes is they're essentially a small kind of many-to-one tutoring style session. So you're able to ask questions, which I'll be able to answer, and we can do some back and forth, and I'll just kind of hold your hand through a particular topic. So we do one of those for year 12 and one of those for year 13 each week. I love doing them, and I really hope I see some of you in there. Lessons. We also have a mixed drop-in session. So in the drop-in session, there's no particular plan. You just come in as if you were coming in to see an online tutor, and you just get to ask some questions and discuss some topics that you're worried about. So you can come in and suggest, or even email beforehand. You can email beforehand like a particular exam question you're struggling with that you'd like to talk about and have me go through. I'll see that email, and I'll go through it with you and with everyone else who's signed in the session. So this is a fantastic feature. This is, again, £50 a month with all of these resources and a kind of comparable tutoring to what you'd get from a private tutor that would be £50 an hour. So it's an amazing value. Really, really, really proud of this. I really hope some of you get involved, and I'll be able to see you in the web classes. And we also have this tutor support chat, which is this option to go beneath each video and again ask these questions, which again is like this kind of one-to-one feedback. So thank you so much for joining me on the web class. Sorry again for the technical difficulties. I hope it was useful, and I hope this is kind of giving you a glimpse into the sorts of things, the exciting things that we're kind of doing for learning here. And I look forward to seeing you in the web classes. Awesome. All right, thank you so much. Yeah, Thank you for sticking with me. Thank you everyone for listening to the lesson, and see you around soon. Okay, best of luck with all your studies, and see you for the next one of these. Okay, bye.